nominations, 9 nominations.
Oh, okay. So, okay, so I didn't prepare slides from before. But I just would like to say a couple of words. So we had actually a record-breaking number of submissions. Number was 7. Yes. Turns out that all of them were outstanding. Okay, so it was very difficult, of course, to make a selection, thinking about that the other could have deserved the award, but one was still standing out for a certain number of criteria, and that's actually Giray's nomination. Just a couple of words about some of the criteria. So he did actually a very, very solid analysis, and then on DRAM interference. And then, well, of course, he will talk about this in more details, but I'm trying to summarize still. After this analysis, so he very thorough and rigorous analysis. So he found some very important and high-profile, how can I say, vulnerabilities, and then proposed countermeasures, very smart countermeasures. And basically, all of this work had actually a very huge impact, in fact, in industry, or is having a very huge impact in industry. And for these reasons, so we thought that would, was making this PhD thesis really stand out. And so I would like to congratulate Giray a lot. So please. And now let's hear about your. Thank you very much.
Okay. Thank you very much for, oh, this is loud. Thank you very much for the award and all the effort that the committee and the whole community put in DSN. So I'm really honored and humbled to get this award. So I'll just make a quick, brief self-introduction. I'm Giray. I'm a postdoctoral researcher and lecturer in ETH Zurich at the moment. And I completed my PhD last year. And in the fall semester, I'll be starting a faculty position at CISPA. And this is the story, I guess. Like I've been doing research in Safari Research Group since 2016. My research interests lie in computer architecture, memory subsystems, hardware security, dependability, and all that. So I want to thank my advisor, Onur Mutlu, and countless mentors that I can just put a subset of them here, and co-examiners whose names abbreviation lucky coincidence makes DSN, and additional letter writers and conference chairs, selection committee, award sponsors, friends and family, of course. Thank you very much. And as I said, I'm really honored to be a recipient of William C. Carter Award. And I'd like to start my presentation with one of his quotes at the conclusion of this paper or there. Until enough data has been collected and analyzed so that we can understand such difficulties, more general and valid theories of fault tolerance cannot be invented. So data collection and analysis is extremely important. Of course, he is talking about a particular set of difficulties here, but I take the liberty to expand it to DRAM reliability as well. So, okay, all my work is about memory reliability. So I'll talk about a concept of memory isolation. So imagine that this is your memory and you perform an access to a location and you observe a bit flip, a bit failure in a different location that you didn't access. You do not want this to happen because it's immediate data loss or corruption. It can compromise your application's correctness. It can be used against you to leak your private information or take over your computer. Data integrity and confidentiality issues may emerge as a result of that. And unfortunately, memory isolation, even though it's a really fundamental principle, it's difficult to satisfy in modern memory chips. And here is why. So as a prevalent memory technology, we use dynamic random access memory, or DRAM. DRAM stores data in the form of electrical charge on a capacitor, and it's a leaky technology, so it's a volatile memory technology. And there's this phenomenon called DRAM read disturbance, where accessing a DRAM cell disturbs other physically nearby cells and exacerbates their charge leakage. This is how we organize DRAM cells in a DRAM array. So we access them in a row granularity. To access data in a row, you need to open that row so that you can access data. To access another row, you need to close this. If you perform this close-open operation many times, then you end up having bit flips all around. And this is a problem that gets exacerbated with density scaling. As DRAM chips get denser, cells get smaller and closer to each other. And existing solutions become prohibitively expensive or ineffective going forward. And we need more detailed understanding of DRAM read disturbance to aid this. So this is I'm just going to flash two papers here. This is a paper from 2014 that discovers this as a widespread phenomenon for the first time. This is not my paper, of course. And then the following year, 2015, Google proposed a new attack in the system level that can use this hardware level vulnerability to take over systems and get root privileges. And fast forward 10 years, this is a paper from last year, again from Google, breaking the Samsung's, one of the major DRAM manufacturers, best practice of mitigating these faults. And they still conduct the same attacks after 10 years. And you can perform these attacks in JavaScript even. And there are works, like there are a lot of works, attack works that I don't have time to cover here, but I want to highlight that if you rely on ECC, the commodity ECC you use that does not actually address this issue. And even in DDR5 systems, we have these bit flips today. Okay, so with this background, I'm gonna talk about a summary of my contributions. So the first one, in my thesis, to effectively and scalably mitigate DRAM read disturbance, we do two things. One of them is build a detailed understanding of DRAM read disturbance. To do that, we look into the sensitivity to temperature, memory access patterns, victim cells, physical location, and voltage. And then we devise novel solutions, leveraging insights into DRAM chip internals and memory controllers. To do that, we leverage the heterogeneity in RowHammer vulnerability across the chip, across chips, and we parallelize preventive actions, and we selectively throttle unsafe accesses. So unfortunately, I don't have time to cover all of these studies. So it's like a cumulative, like 5 papers in top venues. But I'm gonna provide a brief summary, more focused on the characterization part. So this is the DRAM testing infrastructure we have. There are many people's efforts, of course, in building this infrastructure. So this is an FPGA-based infrastructure. We programmed the FPGA with our own design called DRAM Bander. DRAM Bander, and we plug in a DRAM module over there to the FPGA, and we clamp it with heater pads on both sides. And we control the heater pads with a commodity temperature controller, and then we have a power supply to play with voltage on some power rails of the FPGA. And this infrastructure gives us fine-grained control over DRAM commands, timing parameters, temperature, and voltage. Maybe I should just put this here. Okay, in this set of studies, we tested hundreds of chips from 4 major manufacturers, implementing different die revisions, technologies, etc. And to characterize them in the worst case conditions, we did our best effort to eliminate all the noises so that we can observe the bit flips in circuit level. And we perform the worst case access sequence that is known to today. Okay, so these are the 4 studies that I will briefly cover. The first one is temperature. This is a paper published in Micro 21. So what we did here is that we kept testing DRAM chips for RowHammer in different temperatures. So we sweep the temperature from 50 degrees Celsius to 90 degrees Celsius. And we observed that there is a lower bound and an upper bound of vulnerability range. In between, we observe bit flips in a given DRAM cell, but outside of this range, we do not observe bit flips. And this is a quite odd observation in the first look. We call this a vulnerable temperature range. And when we look at the vulnerable cells in DRAM chips, the vast majority follows this kind of trend pattern. Here is some data that I'm not going to go through again, but just briefly highlight something here. So on the x-axis, we have the lower bound. On the y-axis, we have the upper bound. And if you look at this particular cell, it tells us that 4.3% of the cells are vulnerable to RowHammer between 50 degrees Celsius and 60 degrees Celsius. But if you heat up the chip more, then they don't observe bit flips. So it means that if you're testing your DRAM's chip, then you need to test every single cell for every single operating temperature, because you cannot know at which temperature they're vulnerable to RowHammer. And this is why it happens. Some data from the literature. Basically, if you increase temperature, you help electrons move easier, so it gets higher leakage. Reliability gets worse, yes. But it also makes traps lose charge, and RowHammer has a circuit level phenomenon based on trap-assisted charge leakage, and it gets weaker. And which of these leakage mechanisms are dominant is highly dependent on the cell technology, chip manufacturing process, everything. So there's a huge variation, and it's alarming in terms of testing real chips in your production. So I want to highlight another work. This is a DSN work, actually. This is my first DSN paper on voltage scaling. So when we perform RowHammer, we essentially put high voltage on some aggressive rows and then pull them down again. So when we do this repeatedly, high voltage, low voltage, we introduce some disturbance around. And repeatedly toggling the word line voltage leads to these bit flips. And here, what we show is that if we reduce the magnitude of this word line voltage or voltage toggle, then we can reduce RowHammer vulnerability. Of course, it comes at the cost of having DRAM cells weaker. They store less charge and they form like weaker channels. And now you need to operate them in a slower way, and you need to perform more refreshes in parts of it. But it's a method of doing that. So I wanted to mention this as well because I really enjoyed that in the DSN. So, okay. So another part is from the first paper again. It's about memory access patterns. So before this study, the worst known memory access pattern for disturbance was opening and closing rows as frequently as possible so that you maximize the activation count. So instead of doing that, we say that, okay, when we activate, we put a high voltage, and that high voltage creates an electric field. So what if we exacerbate that? So we kept aggressor row at high voltage for longer time. And by doing that, we observe that we can significantly reduce the number of activation count to induce the first bit flip. And that makes existing mitigations ineffective because all of them are configured based on those thresholds. And if the mitigation mechanism doesn't account for this effect, then you can achieve bit flips at lower hammer counts, and you can induce bit flips. And later on, this work paved the way to the discovery of RowPress, which is a new disturbance phenomenon discovered in 2023 that significantly reduces the activation counts needed. And even in extreme cases, we observe bit flips with only one activation. And it's the story in DDR4, DDR3, and HBM2. And we are looking for options to test it on DDR5 as well. Okay. And Samsung also acknowledged that they're aware of RowPress and they're working on that as well. So that's part of the industry impact too. And the last piece of work I want to highlight is the spatial variation aware disturbance. So we tested a lot of cells, actually everything inside the DRAM chip in a DRAM bank, and we observed that if you pick 10% of the weakest rows and say that you need n activations to induce bit flips in those rows, you need at least 2 n activation counts for the remaining 90% rows to induce a bit flip. So this means that if you have a mitigation mechanism configured for the same threshold for all the cells, then you end up overprotecting some of the rows, and this RowHammer vulnerability significantly varies across cells. So our key idea here is to leverage this heterogeneity and dynamically tune the thresholds based on which cells are under attack. And here's an example of mitigation mechanism, para-probabilistic row activation from 2014. So what para does is that when you activate a row, it generates a random number and compares this random number against the threshold. And if the threshold is larger than, the random number is larger than the threshold, then you preventively refresh the victim row, which is a fundamental mitigation operation for this redisturbance. So this is a general trend in like many existing redisturbance solutions in the literature. You always do something and compare it against the threshold. So this is exactly what we do. We provide this victim rows information to our mechanism, and it dynamically changes the threshold so that we can perform less aggressive or more aggressive countermeasures. And we show that it works with like several other mechanisms as well. And when we evaluate the performance impact of this, we observe that we significantly reduce the performance overhead of existing solutions, and it significantly improves the system throughput by this much, and it can be implemented at a relatively low cost. And yeah, okay. So with this, I'm done with like covering part of the thesis. I don't have time to cover all of them, but like this is the full list of papers that I included in my thesis. So so that you will have the link when we share the slides. And I have also 2 talks on YouTube, like 2 hours each, describing all these works in detail. And we have some brainstorming as well in that videos. Okay, so while we were doing that, JEDEC, the body of memory technologies that define the DRAM interface, also formed a RowHammer task force. And the manufacturers' attitude changed. They started with denial of this problem, and then they made more constructive works. And some papers appeared from industry, from Microsoft, SK Hynix, Samsung, NVIDIA, and Google. And finally, last year, we had an update on DDR5 standards that showed the first promising update a decade after the discovery of RowHammer. And I believe that our repetitive characterization works played a huge role on motivating this. And if you look at the recent years, DSN also has some interest on RowHammer. And this week at ISCA, we have a workshop almost completely dedicated to RowHammer and a session based on RowHammer. So with this, I want to share my final thoughts. So redisturbance depends on many conditions, as we showed, and we need more data and more insights to finally solve this problem for good. And unfortunately, testing is costly, and I think going forward, we need better tools, methodologies, including automated reverse engineering tools, online testing methodologies, and crowdsourcing the data collection. And with that, I want to conclude my talk, and thank you very much.
You presented lots of countermeasures. One thing I was wondering, so could some countermeasures be thought of at the compiler level? So that's like, I don't know, or OS level in the terms of memory allocation and so on. So that it at least decreases the chance of these for these kind of attacks.
That's a very great question. So at compiler level, I want to have my reservation. So it's so the problem is you're obfuscated from a lot of system level, hardware level details when you're in the compiler. So you don't know the runtime state of the system, right? So if you think about all this like virtual memory and allocations and how the data is spread across chips, like all these become really hard to predict at the compile time. But compiler can play magnificent role, I guess, to bridge the operating system and the software and the hardware components as well. I think this is a problem that we need to solve in like multi-levels. It really requires some hardware software co-design. So in the current state of the literature, we have very good solutions that can work in hardware and ensure that our data has integrity, but they come at the huge cost of, as Barış also highlighted, like it comes at the cost of efficiency, performance, energy consumption, right? And we had some follow-up works targeting that as well, actually, after my PhD, so I didn't include them. So we identify which processes are performing these kind of attacks, and then providing some feedback to the other parts of the system so that we can do some throttling, for example. That's the easiest thing we can do, I guess. But of course, like more integration with the operating system and malware detection mechanisms is needed. And I think it's like a natural next step that, you know, in the following years, we will see some papers about that. Thanks.
No questions? Abdullah.
Here, actually.
Yours?
Yeah, thank you very much.
You're welcome. Thank you.